All right, Math 5130, moving into something called dummy variables here. So let's pump the brakes a little bit, think back how we interpret coefficients in a model. So the first thing I've done is I want to go back to simple linear regression where we just make a prediction from one variable. So you can see over here in R, I've run that model predicting SSQ from age. And you can see we only get one line in addition to our intercept, obviously, uh, of our estimate. Well, it turns out, again, that negative 2.276 is just the slope. So the interpretation of this would be, as we've discussed previously, as age increases 1 unit, in this case it's in years, the predicted SSQ decreases because the coefficient is negative, the estimate is negative 0.276 units. Now, when we transition this into multiple regression where we have multiple predictors, we can learn a lot from the simple linear regression case. For example, I've called the model SSQ, predicted from age, and HF underscore SCI. And you can see that I have my estimates for the two predictors right there. So if I was going to interpret age, because HF underscore CI is in the model, and I tell you, it would be really nice if we could dive into the mathematics and I could show you that, how we, once I have one variable in the model, how we kind of calculate the extra sum of squares. That would be really cool, but it's just not appropriate for this level. But what I do want you to know, and what is appropriate for this level, is how to interpret a coefficient in a multiple regression setting. So because HFCI is in the model with age, if I'm interpreting age, I would have to say controlling for the other variable in the model, in this case HF underscore SCI. As age increases 1 unit, the predicted SSQ decreases 0.25. Again, decreases because it's negative. If I were to interpret HF underscore SCI, I would say controlling for age, again, controlling for the other variable in the model. As HFSI increases 1 unit, the predicted SSQ increases 1.18 because it's positive. So aside from just adding this first part, controlling for the other predictor or predictors in the model, the interpretation of the coefficient in the context of a multiple regression is the same as interpreting the slope in a simple linear regression. The reason, because it's the same thing. Now, the purpose of this video is to kind of transition from this and think about, well, what if we had categorical predictors? What if we had male-female, or what if we had male-female as entered as zeros and ones, or what if we had males and females entered as M's and F's, or male and female? What if we had facility A and facility B? What if we had these variables that we wanted to enter into our model as a predictor? So enter in something called dummy variables, and I'm not really sure why they're called dummy variables, but it's not because they're dumb, it's just, I just really don't know. But when we have a categorical predictor, we create things called dummy variables, and dummy variables are just when a predictor can be categorized with zeros and ones. But not thought of as numbers. Not like, no apple and one apple, not like a count, but zeros and ones more as placeholders. Now, fortunately, technology handles categorical predictors for us if we make the coding correctly. This works very nicely naturally in R. StatCrunch, we got to work a little harder, but it's not a major undertaking. So you can see that, let's say I would like to add gender to the model. And you might say, pump the brakes, Dr. Darbro. You told us earlier that we needed at least 15 cases per predictor. So if we have 3 predictors, we would need at least 45 cases. We don't have that. We have 43. Well, let's just rock and roll with it. It's just an illustration. But if this was really something that I was interested in studying, other than just in academic exercise, so to speak, that would be a concern. So the very first thing I have to do in adding a categorical predictor to the model is make sure that R recognizes it as a factor. So I add that command, which we've done before. And the next thing I'll call the model, I'll call it model 3, where I have age and HF_SI in the model, and I want to add in gender. So you can see that our model here would be that we would predict SSQ. The intercept is 27.17. I'm just getting this information right here from the table, right? Okay. Minus 0.23 times age, plus 1.28 times HF, and then 14.51 is the gender with the male reference right there. That gender male right there tells me that we are comparing male to female. More about that in just a second. So let's circle back and say, well, if we wanted to interpret this coefficient right here, so let's say we wanted to interpret that one. I would just say controlling for the other variables in the model. So controlling for HF_SI and gender. And then we transition into the interpretation we've had before. As age increases 1 unit or year, the predicted SSQ decreases 0.23 for obvious reasons. Now, it'd be the similar interpretation for HF_SI. I would say controlling for age and gender. As HF_SI increases 1 unit, the predicted SSQ increases 1.28. But how do we handle this categorical predictor? Gender male tells me that R behind the scenes has created this dummy variable with female being 0 and male being equal to 1. Whatever it codes as 1 will be included in the gender name in the output. So in this case, increasing by 1 unit, because that plays a critical role in interpreting the coefficient, tells us what? If I increase by 1 unit, I'm going from females to males, or I'm comparing males to females as the reference category. If my output had been gender female, well, it wasn't, but if it was, it'd be just the opposite. It would be how does female compare to male, because female would be coded as 1 and male would be coded as 0. So the interpretation here would be controlling for the other predictors in the model, so controlling for age and HF_SI. The predicted SSQ for males, because again, what am I doing? I'm comparing up here, because of gender male, I'm comparing male to female. So the SSQ for male is 14.51 because of this number right here, higher than females. Now, how do we handle this in StatCrunch? Let's pop over here, and I'll tell you what, let's just leave it right there. So if I want to handle categorical predictor in StatCrunch, it would make sense I would go to multiple regression, and I would choose SSQ, and I would throw age, FSSI, and gender in the model, but gender is not there. You can work categorical predictors in StatCrunch. It just takes a little bit of work. So what we would want to do, first thing is I'd want to go to data, and I'd want to do a recode. And I want to go down, I want to recode, I want to go right here, I want to recode gender, because that's the categorical predictor I need to create dummy variables for, namely zeros and ones, and I want to create a new column. Now, for female, to mirror the example on the left, I want to code that as 0, and I will code that as 1. Again, dummy variables code with zeros and ones. So I'm going to compute. You can see that StatCrunch is going to create a new column here of genders. As male, it's going to code everything 1. Female, it codes everything as 0. So this is my dummy variable for gender. Now when I go to regression and multiple linear regression, I can predict SSQ from age, HF, and recode gender. I want all the things we had before, like Durbin, Watson, and all the things. But right now, I am just, bear with me, I'm about ready to sneeze. I don't really want to sneeze on. All right, okay, hold on. Oh, shoot. Okay, so I don't really, where was I? I'm really not going to get into this yet. The purpose of this video is just to demonstrate dummy variables or categorical predictors. So run compute, and what you see here is going to look a whole lot like what we got over here, right? And it kind of makes it easier to interpret because we know that male is 1 and 0 is female. So we're comparing male back to female as this notation tells us in R. So again, you notice all the, for gender and everything, that the estimate is the same, the standard error is the same, the p-value is the same. But we just have to work a little harder and code it as zeros and ones. Now, that's about all I want to get accomplished here, but imagine what if our categorical predictor had more than 2 levels? For example, what if, let me make that look clear. What if our, I don't know, what if maybe gender was coded as male, female, and non-binary? What if we had 3 hospitals, hospital A, hospital B, hospital C? What if we had 3 doctors, 4 doctors, whatever? But what if our categorical predictor had more than 2 levels and we are just dealing with zeros and ones? Well, it's problematic, but it does have a solution. All right, my daughter's calling, so I think that means I have to get off here. Talk to you later. Take care.